Okay, so a person stands in an elevator weighing a cheeseburger with a kitchen scale. Okay, so the mass of the cheeseburger is 0.15 kilograms. The scale reading, okay, you gotta remember that scale reading is a normal force. It's equal to 1.14 newtons. I'm just reading this part right here. Okay, that's all I got. Draw a free body diagram showing all the forces acting on the cheeseburger. Okay. Cheeseburger is my little dot. The center mass of the cheeseburger. I got the normal force pointing up, and I got the weight pointing down. Okay, so I don't know if the elevator's accelerating or if it's at rest. Oh, yes, I do. You can figure it out. Because look, scale reads 1.14. Well, let's find what the weight is. Weight, by the equation I gave you, which is a variation of second law of motion, weight equals mass times acceleration due to gravity. So that's 0.15 times 10. That equals 1.5 newtons. Now, we can see that the normal force is smaller than the weight. The normal force is 1.14. Okay, so I should draw the free body diagram to reflect that. Okay, so make the weight bigger. Okay, so this would be part A, right here. Draw a free body diagram, so it's right there. So part B, determine the weight of the cheeseburger. Well, I did that right there. Determine the size and direction of the net force on the cheeseburger. Okay, the net force is equal to MA. I can't use that, so I got to use my diagram. So net force is the sum of these vectors. So which one's bigger? The one pointing down. So it's the one pointing down, the bigger one, 1.5, minus the smaller one, 1.14. So that comes out to be 0.36 newtons. That's the magnitude. And the direction is in the direction of the bigger force. And that would be the weight, which is down. So down is the direction of the net force. Determine the size of the elevator's acceleration. Okay, now that I got the net force, I can go use the second law of motion. So 0.36 equals the mass, 0.15 times A. A equals 0.36 divided by 0.15, which calculates out to be 2.4 meters per second squared. And the direction is the same direction as the net force. So that would be down. So let's do letter E now. At the time that he's measuring this cheeseburger's weight, the elevator's velocity is upward. So this is part E. You got positive velocity, because that positive means upward or to the right, but this is vertical. Speed is the speed increasing, decreasing, or staying the same. Then justify your answer. Well, the acceleration is down, right? So the acceleration is negative, okay? We established that it was down in part, the previous part. So if V and A are opposite signs, then the speed is decreasing. If they were the same signs, the speed would be increasing. So in this next problem, we got the mass of a goose. We have, it starts from rest, so I guess VO equals 0. But after a single step is airborne, okay, whatever. After 2 seconds, so there's a time of horizontal flight, the bird has reached from 0 meters per second. He's reached 6 meters per second, so that's VF. The average drag on the bird during this acceleration period is 7.2 newtons. Okay, so part A, draw a free body diagram of the bird. Okay, so there he's moving forward and he's accelerating. So if you want to think this out, his positive velocity, speed's increasing, so the acceleration also has to be the same sign. So the net force has to be positive as well. So he's going forward, he's accelerating forward. So this applied force, because of the muscles in his wing beating the air, equals, it doesn't equal, that's the applied force. So it's the wind, it's the air molecules being pushed against by the wings. Okay, there's a little bit of drag, but it has to be less because the goose is accelerating in the forward direction. So the applied force has to be bigger than the drag. Okay, other forces acting on him. Well, he's off the ground, and I guess he's going level flight, horizontal flight. So we have the weight of the bird, and it's not normal force, it's not buoyant force, it's lift. Okay, I don't care what you call it, but lift is what you get on a wing that's aerodynamically shaped in such a way that the air underneath it presses up on it. It's not really buoyancy. But anyway, we'll talk about that later. Okay, so there's my free body diagram. The lift equals the weight. But the applied force is greater than the drag. Okay, so there's my free body diagram. Next, determine the following quantities in the, okay, it's acceleration. Okay, well, this goes back to kinematics. I have A, I got VF, VO, and T. So it's really easy. I mean, I'll give you those kinematics. You can use your kinematics equation from the last test. Okay, I'm not going to go crazy on the kinematics, but we should incorporate it since we just talked about it. So 6 minus 0 over 2. That comes out to 3 meters per second squared, positive, because it's in a direction to the right. Okay, so what's its weight? This is number 2. Weight is mg. Do I have the mass? Yes. 4.5 times g is 10, so that's 45 newtons. Number 3. the size and direction of the net force acting on it. Well, that's easy now that I got the acceleration and the mass. Okay, that's m times a. That equals the mass is again 4.5. Now a is not 10, it's the actual acceleration that we calculate right here. So times 3 meters per second squared. So that, I think that's 13.5 newtons to the right. Okay, part 4. The size of the upward lift provided by its wings. Well, if he's flying horizontally, these two vertical forces have to equal each other because he's neither increasing his height off the ground or decreasing it. So lift is equal to the weight, which is I already found in part 2, 45 newtons. Now again, that's because there's no net force accelerating the bird up or down. He's flying at a horizontal path. 5. What's the magnitude of the forward thrust provided by its wings? Okay, this is where the free body diagram is important. I look back at that, and the net force is the bigger one minus the smaller one. So net force is we found to be 13.5 because that's MA. And A is what I'm looking for, the applied force of the wings against the air in pushing the goose forward. And minus the drag. I gave you the drag up here as 7.2 newtons. So therefore, A is 13.5 plus 7.2. So I'm getting 8.6 newtons as applied force. The forward thrust, they called it. Okay, here's a similar to an elevator problem, but they're talking about tension instead of normal force. So we got 25 kilogram mass, little m, upward acceleration. So that'd be a positive acceleration, upward, positive. Determine the tension in the cable. So tension goes up. Now, since it's an upward acceleration, that means the net force is also upward because net force has the same direction as the acceleration that it causes. So I'm going to make tension bigger than the weight because that's how it is. The net force is positive, then the bigger force of the two must be positive. Okay, so what are we looking for? The tension? Tension does not equal the weight, but I do have to find the weight. Weight equals mg. That'd be 25 times 10, which is 250 newtons. Okay, so how do you solve it from there? You gotta go, the net force is the bigger one minus the smaller one. So I'm looking for T. I got the weight, 250, and I can easily find what the net force is using this equation. The second law of motion. So that equals 25 times 2 equals 50 newtons up. So I got 50 newtons up equals T minus 250. So get rid of the 250. So we got T equals 300 newtons. The tension in the cable is 300 newtons up. Okay, let's do the same thing for here, but we're looking at it that it's lowering the downward acceleration. So A is a negative because it's downward acceleration of 2. Here's the mass again. Okay, determine the tension in the cable. Okay, so since acceleration is negative, net force is negative as well because they go together always. The direction of the net force is the same as the direction of the acceleration. So we even can find the net force because they gave me M and A. So that's M A equals 25 times 2 down is 50 newtons down, which because it's negative. Why is it negative? Because the acceleration is negative. So another equation for net force customizes this problem is which ones, well, let's do a free body diagram. Okay, since EF net force is negative, this force has, the negative force has to be bigger than the positive force. So this is the weight, this is the tension. Well, the weight equals mg equals 25 times 10 equals 250 newtons. So this would be the bigger one. Net force would be the bigger force minus the smaller force. And I have some 50 down, 50 newtons down, I figured that right there, equals 250 minus T. I'm gonna subtract 2, let's add T to both sides. Okay, so 250 is equal to T plus 50. And then I'm just gonna subtract 50 from both sides. So 200 is equal to T. Okay? This next one is elevator problem. We set these up in class already. So let's figure this out. Here's the mass. Scale reading. Okay, the scale reading is a normal force. If the elevator has an acceleration, okay, this is 4 different problems. So this is part A. Acceleration is 1.8 meters per second squared up. So we're doing this. That means the net force is up, is positive, is up. And so if the net force is up, the force that points up is bigger than the force that points down. So talking about a guy in an elevator, it's not tension, it's normal force going up and weight going down. Let's find the weight. The weight of the guy is mg 71.4 times 10 equals 714 newtons. Okay, so net force, I got M and A, so I can solve it that way using second law. 71.4 times A. Okay, that equals 128.5, 129 newtons. Okay, the net force, remember that's up. Okay, so net force is N minus the up one minus the down one. So because up one's bigger, why? Because the up one is in the same direction as the net force, which is in the same direction as the acceleration. Okay, so this be N minus W. So I got 128.5 equals normal force, the scale reading, minus the weight, which is, I did that already, 714. Okay, I'm going to add 714 to both sides, isolate unknown. I'm going to get the normal force or the scale reading. It's going to read 843 newtons. So 843 newtons is the normal force. That would be the scale reading. So let's do part B now. So it's the same numbers. So let's see how it's different. So A is negative 1.8 meters per second squared, or 1.8 meters per second squared down. Okay, so F net is also negative. Okay, so we can draw our free body diagram so that the negative force of the two is bigger than the positive force. Okay, again, you always make the force that is in the same direction as the net force is the bigger one. So net force equals weight minus normal force. The net force is still the same as MA, which we did over here. Where is it? No. I didn't show it. It's M times A. Okay? So I did that work already. So that equals 128.5 newtons, but is down. So I got to take the bigger thing, which is the weight, and subtract the smaller thing from it. So the weight is still 714. I solved that up here. Minus the normal force. So the normal force, let's add to both sides. I get N plus 129, I'll just do that, equals 714. Then I just subtract the 129 from both sides. And you get the scale reading is 714 minus 129. 714 minus 129. I get 585. So the scale reading reads less than his actual weight. 585 compared to 714. Okay, part C. This is kind of, you don't really have to work this one out. We should know how from just figuring it out. If your acceleration is negative 9.8 or 10 down, I should just round that up to 10. Your net force will be your weight. So let's do part C. Let's do it in black. Okay, so The acceleration is, can I just say 10? Make this easier. Okay, so it's 10 meters per second squared down. So the net force is down. And so, or negative, that's what I mean by down. Okay, and so my free body diagram, I got the weight being more than the normal force. Okay, I have the weight already up here. I did it as 714. And so net force is equal to MA again. So that would be, the mass is still 71.4. And the acceleration is 10 down, negative 10 if you want. So that comes out to be 714 newtons down. Okay, so sum up. The net force also equals, in this case, the bigger one, weight minus normal force. Net force is 714. The weight is 714. This is weird. Minus N. So N is 0. There is no normal force. You feel weightless. So think about that. If the elevator is accelerating downward at the acceleration of free fall, well, the elevator is freely falling, and you in the elevator are freely falling. If you're freely falling with the elevator, the force is not pushing up against you. Both of you are freely falling. So that's kind of a cool case there. The scale would read 0. And then letter D, what if you had no acceleration? That's really easy. It should be, sorry. So letter D, I don't even have to do that much work for that. Acceleration is 0. There's no net force because the forces are balanced. My free body diagram would have N equals the weight. So your normal force would equal the weight, which is equal to still 714. The scale would just be reading your weight as if the elevator was stopped. Now, it could be stopped if acceleration is 0. It could be stopped at rest. It could be moving up at some constant speed, or it could be moving down with some constant speed. We don't know. We just know the acceleration is 0. Okay. So we have a helicopter accelerating downward. Okay, that's what the 2.5 is downward. What is the lift force exerted by the air on the rotor blades? Okay, well, that's like normal force. Don't freak out, it's not that much different. So we have the normal force. Okay. And we have weight. That's it. So what is the lift force? So I'm not going to call that normal force. I'm going to call it lift. Basically, that's similar, but not the same thing as normal force. It's upward force. So I'll call that lift. Okay, they do not equal. If they did, it'd be moving at constant speed. So weight equals mg. Mass is 3,500. G is 10. So we're looking at a big number, 35,000 newtons. So which one's bigger, the lift force or the weight? Well, the acceleration is negative, so the net force is negative. So of the two forces, the negative, the one pointing down, downwards means negative, is the bigger one. So I better make the weight bigger on my free body diagram. Okay, so here's the weight, let's say. So, what's the lift force? Well, you have to go now to the other way. Let's write it. The lift force, the net force is equal to the bigger one minus the smaller one. So, net force is, another equation for net force is ma. I have the mass, 3,500, and I have the acceleration, 2.5. So, net force, 3,500 times 2.5 is 8,750. Now that is downwards. So we have that now. We can plug it into the other equation for net force, customized to this problem, that equals the weight, 35,000 from up here, minus L. I add L to both sides, and then I subtract 8,750 from both sides. So 8,750 plus L equals 35,000. So L is equal, subtract 8,750 from both sides. And I get 26,250 newtons of lift force. So the rest of these questions have to do with the second positive physics for this test 2A. So I'll be teaching this after Kairos. A box of mass. Okay, here's the mass. Push horizontally, which I'll say to the right of 255. Oh. Let's continue to just use symbols, so I don't have to write as much. So that's the applied force, the pushing force. So that's A, capital A. Acceleration is to the right, and it's positive. Where's the value of the coefficient of kinetic friction between the box and the floor? Okay, so we got weight, we got normal force, but they all balance out. The normal force and the weight balance out because it's not accelerating up or down. And since they're talking about friction, there must be some friction here. Okay, so I'm assuming this is accelerating in the positive direction. So, which of these horizontal forces is bigger? Applied force or friction? Well, if you have a positive acceleration, the positive force, which is acceleration, the forward, the one that points to the right, is bigger. So let's write my two equations. F net equals big A minus little f. And then I can also let's just do two birds in one. Let's get two birds with one bag. Okay, so this is MA. F net is MA equals big A minus friction. Okay, I know big A is 255. I know the mass is 25. Acceleration is 3.5. So doing the math, I get 87.5 equals 255 minus friction. And so let's add friction to both sides. So I'm going to get friction plus 87.5 equals 255. So friction equals 255 minus 87.5. Which comes out to be 167.5 newtons. Okay, so what's the coefficient of friction? Of kinetic friction? Well, that equals the friction over the normal force. Friction over the normal force. So I just got the friction as 168. And isn't the normal force equal to the weight? And the weight is mg. The weight is 25 times 10, let's say, is 250. So n equals weight, so that'd be 250. 168 over 250 gives me 0.67. There's no units on coefficients of frictions. Okay, let's look at this one. I'm going to go right up here on this one. So it puts okay, there's the mass against the vertical wall, like I showed in this picture, with a force of 26 newtons. Okay, that's the applied force. The book does not move. Now, I'm pushing it as lightly as I can. So I want to find what's the minimum coefficient of static friction on this wall. So that is mu s, right? Mu s is F over normal force. Now let's draw the free body diagram. Here's the book being pushed against the wall. I'm applying that force right there, perpendicular to the wall. Okay, there's a normal force of the wall pushing against the book, right? And it has to equal, according to Newton's third law, action-reaction law, they have to equal each other. Okay, so there's the weight of the book, right? And then there's the friction. And those must equal each other, or else it'd be either rising, sliding up the wall, or probably sliding down the wall if there's not enough friction. So I'm at the point where if I pushed it any lighter, if I had any smaller A, it would start slipping. So what do I know? I know the weight of the book, mg. That's 0.8 times 10. That's 8 newtons. Now I should have told you that this right here is the minimum force needed to keep the book from sliding. So if I pushed any harder, it would just punch more into, it would just stick better to the wall as I held it. But if I pushed any less, it would slip off the wall. So let's figure out. So that applied force is 26 newtons. So from what because I'm pushing the book against the wall's pushing back with an equal amount of force. So it equals A, which is 26 newtons in the opposite direction. So I need to find the coefficient of friction, but before I do that, I need to find the friction. Look at this equation. Well, I know what the friction is. It has to balance out the weight or else the book would slip down. So I know the friction equals the weight because this book is at rest, being pushed against the wall. So that also equals 8 newtons. So we can now go down to here and plug in the numbers. The minimum, the friction is 8. The normal force is 26. So 8 divided by 26 comes out to be 0.31. Okay, so 0.31 is the coefficient of static friction. Okay, it looks like I forgot this one over here. So before I do that problem, let's look at a situation where something's sitting on another surface and there's friction between those two surfaces, a block and the table, let's say. As we apply a force, the friction matches that force. So I apply a bigger force, that friction continues to match that force until it hits a limit. Okay, when the force gets to this critical limit, the friction, we call it static friction, won't be enough to keep the block in place. And we call that the maximum static friction. And at that point, the block will start moving. And once it starts moving, it's gonna move. The friction's gonna decrease to kinetic friction, no matter what the applied force is. And that kinetic friction will be less than the maximum static friction. So here we have a shoe, a guy's running, and hopefully his foot's not sliding over the surface he's running on. So let's say the fastest he can run with this friction between his shoe and the ground, we're going to talk about he's going to run so fast that his force pushing against the ground will be equal to the friction, the maximum static friction. So let's see, the shoe wants to slide that way, right? So the friction would be this way. And so, again, his shoe wants to slide that way. It's not doing it, but the friction opposing it is pointing to the right. So that's my free body diagram. He is pushing against the ground, but I'm not going to show that force because it's against the ground rather than against his shoe. So all we got to do is we're looking for the acceleration, the maximum acceleration. So net force is equal to ma. The mass of the guy is 62. I'm looking for A. So I have to use another equation for net force. Well, the net force is equal to the friction, the maximum static friction. So the maximum static friction is mu times the normal force. So that's static coefficient of friction. Normal force is actually going to be the weight. Simplify this. This is equal to the weight. And the weight is equal to mg. So the maximum static friction is equal to the coefficient of friction. It was given in the problem, 0.7 times the mass of the guy, 62 times 10. So that is equal to the net force, because the weight and the normal force balance cancel out, supposedly. Okay, so we can now put this in here. 0.7 times 62, 0.7 times, actually times 620 is 434. So 434 is equal to 62A. So A equals 434 divided by 62. That comes out to be 7 meters per second squared. Okay, let's do an easier one, number 10. So here's the mass of the baseball player. Here's his VO. Looks like we're going to have to do a simple kinematics equation. He slides into home plate for a distance. Okay, there's delta x, or distance before coming to rest. Vf is 0. Calculate the coefficient of kinetic friction. Since he is sliding, they're looking for a coefficient of kinetic friction between the guy, the base runner, and the clay. Okay, so here's a picture of the base runner. Let's say he's running forward. Okay, he's going to the right. So he's sliding, so there's no force pushing him to the right. He was running, and that speed continues until he hits the ground, and then it slows him down. So there's the normal force. Here's the weight. There's no forward force, okay? But there's friction, the kinetic friction, in the opposite direction of where it was moving. So these two guys cancel out, and the net force would equal the friction, kinetic friction. Okay, so I'm supposed to find, so the net force is equal, okay, Fk, right, is mu times n. N is the normal force. So once again, the net force would equal that. And so that would be what I'm looking for. So net force also equals MA, right? Now, so we could put that right here. Net force, like what I said, net force equals Fk. Net force equals mass times the acceleration as well. Okay, so mass times the acceleration equals Fk. So I could just, these two guys, net force equals Fk, and net force equals Ma. So I can just put them together. So let's keep on going like this. Oh, the G's cancel out. His mass didn't even matter. That's pretty cool. So mu K equals A divided by G. Okay, so all we have to find is A. A equals VF minus VO over T. Yeah, but I can't use that one. So I'm going to use, it's because I have delta X up here. I got VO, and I got VF. So, delta X. Let's see. VS squared equals VO squared plus 2 acceleration times delta X. So VF is 0. VO, 2.8. That's not very fast. And then 2A times delta X. 3.8 is how much he slid. So 2.8 squared equals, okay, let's show all the steps. 2.8 squared plus 7.4 A equals 0. So I'm going to just subtract 2.8 squared from both sides of the equation. So the acceleration equals negative 2.8 squared divided by 7.4. So the acceleration is equal to negative 1.06 meters per second squared. Okay, but it's not going to matter when I put it back into this equation that it's negative. So mu K equals 1.06 divided by 10. So mu K is equal to 0.11, no unit. Okay, that's kind of slippery. Okay, so the final kind of questions. The box sits on the horizontal bed of a moving truck. Static friction between the box keeps the box from sliding. Okay, so the truck is accelerating to the right. So the box wants to slip. It wants to slip backwards because it's an object that in motion remains in motion. An object at rest remains at rest relative to the floor. And if the truck goes forward too fast, it will slip backwards. That means the friction will be facing that way. So as the car accelerates, the truck accelerates forward, the static friction builds up until it's the maximum static friction, and then it will start to slip. So that's the situation for the friction. That's also the net force acting on it. Okay, so let's solve the problem. What is the coefficient of static friction between the crate? If the crate just starts to slip when the truck is accelerating at a rate of 4 meters per second squared. So that's the A. So they're looking for what is the coefficient of static friction. Okay, coefficient of static friction is the static friction over the normal force. Well, the normal force is equal to the weight is equal to mg, right? So drew the picture. Here's the weight, Here's a normal force. They equal each other. And there's the friction. The maximum static friction. Okay, so this static friction is also the net force, because N and W cancel out. Normal force and weight cancel out. So, so I'm stuck with that. But I also know that the net force is equal to MA. I got the mass of the box, don't I? No, I don't. So it's M times 4. 4M is the net force. Hopefully the mass will cancel out. Do they tell me the mass? No. Okay. So I can now say, okay, static friction max over N is what mu is. Okay, here's where it cleans up. So, since N is mg, I can say this is Fs max over mg. So, F maximum static friction is equal to mg mu s. Okay, so also you realize that the net force is equal to the friction, like I said up here. It's the unbalanced force. So that, let's equate these two equations right here. So 4m from right here, net force is equal to Fs max, which is mg mu s. The m's cancel out. The mu s is given, is what I'm looking for. I'm sorry, is what I'm looking for. So that'd be 4 divided by g. Acceleration due to gravity on Earth is 10. So 4 divided by 10 equals 0.4. That's the maximum static coefficient friction between the box and the crate. The crate and the bed of the truck. Well, that's pretty, one's the highest, so that's not really sticky for a coefficient of static friction. So I would strap that thing down if you're going to be accelerating, crazy acceleration with the truck. Or else it's going to slide around. Okay, let's do this one. Okay. So we got an acceleration that way of 3 meters per second squared. So it's negative, so it's going to the left. Okay, I am assuming that the box was at rest. And since it's at rest and then starts acceleration in the negative direction, I'm assuming the box is going to be moving to the left. Okay? So the acceleration to the left is picking up speed, okay? So we can tell that the friction, therefore, will be pointing to the right. And that'd be static friction. Well, it's already moving, so that'd be kinetic friction. So I'm asking how much force did person B apply while it's moving. Of course, he applied bigger force to get it moving, but that's not what I'm asking. So I'll be more specific. Also, I said the coefficient of kinetic friction is 0.2. So right away, I can figure out mu equals F over N. N equals weight equals mg, right? Got N, we got the weight pointing down. They cancel each other out. Okay, so we can say that mu equals F, which I'm trying to find, so I can use it, over mg. So friction equals mug, mug. So we got 0.2 times the mass of the thing, which I didn't give you, so, oh yeah, I did. The box is 50 kilograms times 10. So 500 times 0.2 is 100. So, okay, so that FK is 100 newtons. Okay, so this guy, you can probably look at it and just tell me the net force is equal to MA, right? So, the net force also is equal to applied force from B minus the applied force of A minus the kinetic friction, right? So, sorry, this looks a little confusing. So, applied force of B, I could just say F of B, and the applied force of A minus the applied force of A and the friction. So let's just substitute numbers in. Net force is MA. I know M is 50 and A is given as -3, but I'm not going to put the negative in because this is dynamic, so this is 150 newtons. So this comes out to be 150 equals AB, which is what I'm looking for, the force, applied force of B, minus A. I know that's 100. FK is 100. So we're going to do the math here. 150 equals A minus 200. So A is going to have to be 150 plus 200 newtons, which is 350 newtons. So that's what the force of A is going to have to be. I'm sorry, the force of B have to be. The applied force of B has to be 350 to the left. Okay? And that's it.